Welcome to Molecular Interactions. So, real gases do not obey the ideal gas law exactly, except in the limit of pressure approaching zero. So, real gases exhibit significant deviations from the ideal gas law at high pressure and at low temperature. Remember that the kinetic molecular model assumes that molecules occupy no space. That means their diameters are negligible compared to the distances between the molecules. And this means that at high pressures, this assumption is not true. Because at high pressures, those molecules are packed close together. And this means that the volume of the gas molecules starts to become a significant fraction of the volume of the container itself. That is, the repulsion between molecules becomes significant. Because once those molecules start to occupy a sizable fraction of the volume of the container, that means that the real volume left in the container, the unoccupied space inside the container, is now significantly less than the volume of the container itself. Also remember that the kinetic molecular model assumes that the molecules are only interacting during the collisions themselves, and that they're acting independently otherwise. Furthermore, it says that those collisions are brief and infrequent. That means that the vast majority of the time, those gas molecules are not interacting with one another. Now, at low temperatures, this assumption breaks down. It's no longer valid because the molecules are moving relatively slowly, and that means they're moving slowly enough that the intermolecular forces start to become significant and start to alter their trajectories. That is, the attraction between the molecules becomes significant at low temperatures. So, as those molecules start to attract one another, that means that they're going to become closer together than they otherwise would. If there was no attraction there, then their trajectories aren't important. But this means that at lower temperatures, now the pressure is going to be smaller than it otherwise should be. So the compression factor, or capital Z, of a gas is the ratio of its measured molar volume to the molar volume of a perfect gas at the same temperature and pressure. So Z is equal to V sub m, so the molar volume of our gas as it is, divided by V sub m naught. So that's the molar volume of a perfect gas, or an ideal gas. So for an ideal gas, Z is equal to 1 at all conditions. And that means that deviation from Z equals 1 indicates deviation from ideal gas behavior. So a Z less than 1 indicates that the gas is experiencing an attraction dominating conditions. So this is low temperature or moderate pressure. Z greater than 1 indicates that the gas is experiencing repulsion dominant conditions. So this is going to happen at high pressures. And so you can see that as the separation between our molecules decreases, we enter this attraction dominant zone. This is for a fixed temperature. And those molecules, as they get closer together, they attract each other, and they attract each other more until they start to repel each other. And now, at this point now, the repulsion, those repulsive forces overcome the attractive forces, and now it goes back up, and the potential energy gets to zero, and then the potential energy becomes much, much higher. Basically, now those molecules have come into contact, and now they're really pushing against each other, and that will just keep going up to infinity. And out here, it asymptotically approaches zero. As you get those molecules infinitely far apart, that attractive force between them is zero. Now, we can also relate the compression factor to the ideal gas law. So, P times Vm is equal to RT times Z. Now, the behavior of some real gases is plotted over here. And you can see there's an inset here. So on the bottom, we've got pressure. And on the left axis, we've got the compression factor, Z. And in the inset here, it zooms in on that region there where we have low pressure. So note that down here, we've got numbers of 200 atmospheres, 400 atmospheres, 600 atmospheres, 800 atmospheres, and up here, this point is 10 atmospheres. So if we're looking at 1 atmosphere, we're way over there. So all of those compression factors are pretty darn close to 1. Note that even down here, we're still only at a compression factor of 0.96. So you can see that for most gases, we've got this attraction-dominated zone down here, where as the pressure increases, those molecules start to attract each other. They're now no longer so ridiculously far apart. Now they're close enough together that they're starting to attract each other even closer. And that means that our compression factor is below 1 until we reach the bottom there. And at that point now, the repulsive forces begin to overtake. And when we get back up there, now it's acting like an ideal gas again. And then in this zone, those repulsive forces are now more important, and that gas occupies a larger volume than the ideal gas would. Note that here, hydrogen does not have that attraction-dominated zone. The compression factor for hydrogen is always above 1. So the deviations from ideal gas behavior can be predicted by this equation. So we've got pressure times the molar volume is equal to R times T times this quantity, where now we have 1 plus B prime times P plus C prime times P squared, and so on. So we'd have D prime plus pressure cubed. And a more common form of this is P times Vm equals RT times the quantity 1 plus B over Vm plus C over Vm squared, and so on. Now these two equations are two versions of the virial equation of state. And note that the term in parentheses is simply Z. So P times Vm equals RTZ, and now we've expanded out that Z term. Now those coefficients, 1, B, C, and so on, are the virial coefficients, and these depend upon the temperature. Now the early coefficients are usually the most important, and that is at most values of the molar volume, C divided by Vm is much less than B divided by Vm. And that means that usually we can ignore the C, D, and so on terms. We're just looking at the B term. Now, note that while the equation of state for a real gas may approach that for an ideal gas as pressure approaches 0, not all of its properties necessarily approach those for an ideal gas. For example, the change in compression factor with respect to pressure for an ideal gas is 0. But for a real gas, dz dp is equal to b prime plus 2p c prime, and so on. And that means that the limit of dz dp as pressure approaches 0 is approaching b prime. Now b prime is not necessarily 0, so that means that the slope does not necessarily approach 0 for a real gas, as can be seen in that plot that I showed earlier. Now similarly, the limit of dz d 1 over Vm, so 1 over the molar volume, as the molar volume approaches infinity, approaches B. Now because the virial coefficients depend upon the temperature, there may be a temperature at which Z approaches 1 with 0 slope at low pressure or high molar volume. And this temperature is called the Boyle temperature, T sub B. And at this temperature, the properties of the real gas coincide with those of a perfect gas as pressure approaches 0 and B is equal to 0. At the Boyle temperature, the behavior of the real gas closely matches that of the ideal gas to higher pressure than at other temperatures. Now let's look at condensation. As we compress a sample of gas, and here we're going to use carbon dioxide, at constant temperature by pushing on a piston, the pressure of the gas increases. So we're over here at point A. As we press on that piston, the pressure of the gas inside is going to increase. So on this curve, we've got an increasing pressure as we lower the volume. Now, at some point B here, the non-ideal behavior of the gas becomes significant as the molecules begin to attract each other, and the pressure increases slower than we expected it to. And now, at point C, which is here, all similarity to ideal behavior is lost entirely, and the piston slides in without any increase in pressure. Now, just to the left of point C, so right there, a liquid appears, and there are now two phases. We have a liquid phase and a gas phase. And there is a sharply defined surface separating the liquid from the gas. Now, as the volume is decreased from C here, past D, and over to E, the amount of liquid increases and the amount of gas decreases. There's no resistance to that decrease in volume because our gas responds simply by condensing. So we're not increasing the pressure. And note that the pressure at this point is the vapor pressure of the gas at that temperature. Because of course, if we have a liquid in equilibrium with a gas at some temperature, then that gas must have the vapor pressure of that substance at that temperature. Now, once we've reached point E here, the substance is entirely liquid and no gas remains. And the piston now rests on the surface of the liquid. So even a small decrease in volume means that now we're trying to compress that liquid, and that now causes a very rapid increase in pressure. From point E here, we're going not quite vertical up to F. Now, note that liquids are indeed compressible in contradiction to what you may have learned in previous classes. You may have learned in previous classes that you can compress a gas, but you cannot compress a liquid or a solid. That's not true. You can compress a liquid, and you can also compress a solid. It's just that they compress to much, much smaller extents than gases do. That is, as you increase the pressure by some amount, that liquid is going to compress a very small fraction compared to the fraction that the gas compressed to. So these lines keep going up and up and up as we decrease the volume. We're going to have to put much, much more pressure on. So now let's examine the pressure volume curve. This is the isotherm for carbon dioxide at 31.04 degrees Celsius. So that is now not these labeled points A, B, C, D, E, but now we're looking at this curve, that curve immediately above. So this is a special temperature because the curves for the temperature below this value exhibit behavior similar to that we've seen earlier, where we reach this point and we condense our liquid phase out, and we now have this flat section in there where as we lower the molar volume, we do not increase the pressure because we're simply condensing the liquid. But at this temperature, that 31.04 degrees C, there is no surface separating the liquid from the gas. Instead, at this temperature, the two ends of the horizontal line that represents that condensation have now merged to a single point right there where the star is on my plot here. They've merged to a single point that we call the critical point. Now, the critical point defines the critical temperature, T sub C, the critical pressure, P sub C, and the critical molar volume, V sub C, which are collectively the critical constants of that substance. So at and above Tc, the sample has a single phase that occupies the entire volume of the container, no matter what that volume is. This phase is, by definition, a gas, and that means that the liquid phase does not form above the critical temperature. Now, since the density of this phase is generally much denser than what we would typically consider a gas, we use the term supercritical fluid instead of gas to describe the system at that point. And that was molecular interactions.